oddly enough. Okay. Hi, Dong Ting. And everybody else. Cool. I think we are in. Apologies for the slightly late start. So the plan today is to mostly focus on the exam. So I posted the take-home part last night. We'll go over that today. And then the in-class will be on Wednesday, and we'll see what kinds of questions people have about that as well. So my plan is to start with going over the take-home. But are there any questions about anything else before we do that? Any questions online? Questions here in the room? No. Okay, well, let's look at the take home then. So I'm going to share my screen. So the take home's got four problems organized into two groups. And the first is essentially a string HTML problem, and that the last three work together to do a sound thing. Okay, and so we'll go over what all those look like. So one thing we didn't talk about in HTML is how to make lists. And you've certainly seen lists on web pages before, so it wouldn't probably be a huge surprise to find that you can make lists in HTML. And lists come in two forms in HTML. And in fact, they come in two forms in a lot of computer-based layout systems. What's called an unordered list, so a list that doesn't have an order assigned to it. And those are usually displayed with bullets. And then an ordered list, which are usually displayed with numbers or maybe letters or maybe Roman numerals, right? There can be different ways that the counting is represented, but there is the idea that there is a particular sequence and that there are numbers attached or labels, ordered labels attached to the items, okay? And I linked to a description of how this is done on W3 Schools. So you got that reference. But I also have examples back here. So I'll actually walk through just what I've provided, but there's plenty of documentation online if you end up with questions. And of course, you can ask me. So the big thing between an unordered list and an ordered list is an unordered list uses the UL for unordered list tag, and the ordered list uses the OL for ordered list tag. Pretty straightforward. Okay. And so this eggs, milk, crackers, numbing locally grown carrots list is an unordered list. So we would have an open UL and a close UL. Okay. Those say we're starting an unordered list and we're ending an unordered list. And then we have the items. So we say we're starting and ending a list, but we also have to say what the items actually are. And we do that with the LI tag. The LI tag, that stands for list item. These sort of abbreviations aren't super obvious, but they make sense sort of once they're explained. And you have an open LI and a closed LI that are like, we're beginning a list item, we're ending a list item. And notice that this allows us to have long, complex things in a list item. So we can have a multi-word phrase, we can have a whole sentence. In fact, you can have whole paragraphs. You can have lists inside of lists. So inside of an LI, you could start another list and have items and close that list and then close the LI, and that would give you sublists. we're not doing anything that fancy here, but you can put pretty much arbitrary HTML between the LI and the close LI. We'll just be putting strings there that generally won't be all that fancy, but in theory, you can do some pretty complex stuff. So here we have an unordered list that has 4 list items: eggs, milk, crackers, and numbly locally grown carrots, and that would give us this piece of HTML here. And in fact, while it's not really all that crucial, a web page like this in Canvas is actually just HTML. And Canvas gives you kind of a fancy editor to simplify making these things, but you actually can go in to look at the raw HTML and edit it in Canvas. If the fancy editing tool doesn't give you all the things you need, there is a link that you can click that's, I think, Edit HTML or HTML Editor, sort of on the top right. And it will actually show you the raw HTML. It's not very pretty. Their editing tool does not generate the most elegant of HTML, but you can then go literally directly hack the HTML if you want. So if we open this up, we would see a UL, close UL, and 4 LIs, very similar to what I've done here. Now, an ordered list is the same sort of thing, but it's just OL instead of UL. So we've got OL, close OL, and 4 list items: introduction, background, the part where I attempt to make a compelling argument, and conclusion, which is the outline of most papers ever written at university. Very similar structure, okay? Now, are there questions about what we've seen so far? Any questions about sort of the structure of lists in HTML? Questions about any of this? Going. Cool. Then I should say, I've indented these just to make them easier to read. But again, HTML doesn't care about white space and indentation. So in fact, these could all just be one long line, okay? So here I've got the grocery list example just as a single line, and this would work just as well. The web browser would display that the same way that it displays this more nicely laid out one here. You would get exactly the same behavior. And it's probably easier when you're writing Python code to generate a list, to just make one big long line than to worry about like, how would I format it nicely? And so most machine generated HTML, which is most of the HTML in the universe these days, isn't very pretty to look at because it's just been generated by a program where the concern was not making it look nice, but instead was to sort of simplify the programming side of things. In the early mid-90s, when most HTML was being generated by hand, a lot of it did look like this, where you had nice indentation and it looked rather pretty. But yeah, nowadays it tends to, if you look at the source of a web page, it tends to look like this, or worse, because so much of it is JavaScript and other crazy tools that we're not going to worry about today. Okay, so questions about the basic ideas of lists in HTML? So then problem 0 is you are writing a function that makes a list. You're not actually having to put this in a web page. If you want to, you can, right, for your own, just to be able to look at it. So if you want to like wrap this in a body tag and open it in a web browser, that'd be great, right? Just for your own sanity. But all I actually am asking you to do is write make list. And make list takes 2 arguments, is ordered and items. Is ordered is a Boolean value. We haven't done a lot with Booleans. We've mostly done things with numbers and strings. But Booleans are a legitimate type in Python. And a Boolean is where a number can be like 0 or +7 or -32, and a string can be the empty string or Ted or Jane or Heffalump. A Boolean only has two possible values in the world, true and false. And we can use those often to indicate when we want something turned on or off, for example. And here we're using it to indicate whether we want the list to be ordered or not. So if is ordered is true, then the list should be true, or should be ordered. And if is ordered is false, the list should be unordered, UL, okay? And then items is a list of strings, okay? And you can just assume it's a list of strings. You don't have to worry about the contents being anything interesting. And so you should take those two arguments and return a string that would generate an appropriate list given those inputs. So if I say make list false and my grocery list here, then I should get an unordered list because it said false, so it should not be ordered. So I've got a UL and a close UL. And then I've got my list items, one for each item in the list. So you're going to need to have some kind of for loop over the items in the list. For each item, you'll need to put LI, close LI around it. And then you'll need to append all that together and then put a UL or an OL around it, depending on the value of the Boolean at the beginning. You're welcome to use things that we did in class or things that are in the book. When the book talks about HTML in chapter 12 or whatever it is. So like if you want to use the wrap in tag function that we went over in class to help simplify putting the LI tags around an item or the UL or OL tag around the whole list, you're welcome to do so. You don't have to. Right? You're not going to be graded on your use of the stuff that we did in class, but you're certainly welcome to use all that stuff. Don't feel like you have to reinvent the wheel here. That is not the goal, right? Use the tools that you have. If you built anything for the Mad Lib assignment that you think would be useful here, feel free to use it. That's totally fine, okay? So does that make sense? Questions about the make list assignment? Now I'm gonna, if there's time, I might come back to this and talk a little bit about Booleans, but I want to get through the rest of the exam first. So questions anywhere? Questions online? Are we good? Questions here in the room? No? Cool. Let us roll then. So the next set of exercises are collectively doing a specific thing. So it's a group of steps that solve a particular, well, I don't know if problem is the right word, but do a thing that I decided it would be fun to do. So we're going to take a sound and we're going to modify its frequency and add sounds together. So let's imagine we've got this initial sound wave, okay? And this is, really this is a sound. I'm just using the sound wave as a way of representing it visually in the write-up. This is actually the sound wave for the almost sound in the files the book provides, or always. I don't remember if it's almost or always now, but it doesn't really matter. But it's one of the sounds provided in the book. If we double its frequency, okay, and we went over that in class, there is a solution to doubling frequencies in the book in chapter, I think, 9. So doubling the frequency is a thing we've seen. And we double the frequency essentially by throwing away every other sample to make it go through the samples twice as fast. And if we double the frequency, we get a graph that looks like this. So the amplitude has stayed more or less the same, but we get through all of the stuff twice as fast. Now, one thing that means is that this sound is half as long as the original sound, right? If this was, let's say, 4 seconds, it's not anywhere near that long, but it'll make the math easier. This was 4 seconds. This new sound would be 2 seconds long, right? If this was 400 samples, this would be 200 samples. Does that make sense? Questions about that? Okay. Now, that means that if we take 2 of these and join them end to end, we get back to something that's got the same length as the original sound, right? If this goes from 4 seconds to 2 seconds, or 400 samples to 200 samples, we take this and stick 2 copies together, right? We're going to get a sound that's now 4 seconds again, or 400 samples, right? Because we're going to get something that's twice as long as this was, and this was half as long as that. Does that make sense? And now, because these things have the same length, we could merge them together, right? Without worrying that one's going to end before the other. They have exactly the same length, so we could merge this guy here with this guy here and see what that sounds like. But to complicate things even further, we're going to do this a second time and double the frequency of this guy. So that will be 4 times the frequency of the original sound. So if this is twice as fast, we double it, it'll be 4 times as fast as the original sound. And so we get a stack that looks kind of like this. Here's the original sound at the bottom. We've doubled the frequency and tacked 2 of them together. And that's the same length as this. And then here, we've doubled that yet again and tacked 2 of them together, or 4 of them together, depending on how you want to think about it. Because you can think about this as we've taken this and multiplied it by 4 and then made 4 copies. Or you could think of this top one as this middle one sped up by a factor of 2, which would give us this much. And then we take 2 copies of that and join them together. However you want to think about it, doesn't really matter. But all 3 of these have the same length. That's really the crucial piece, okay? So we can then add them together and we get, in this case, something like this. So where there's this long empty tail in the original one, there's now a bunch of sound here, and then also some sound here, but it still has a bit of a tail here that is in quiet in all 3 of them. And so you can see that's that little bit right here, okay? So this is the sum of all 3 of these divided by 3. Because if we just add these together, we might get some clipping. Because if the loud part of this lines up with the loud part of this, lines up with the loud part of this, we might go above 256, or sorry, 32,567, and get some clipping. So I'm adding them and dividing by 3. So the average volume stays the same. And so we can get something like that. Oh, and this was apparently the always sound. I don't know what I said earlier, but, and so if we listen to this, and I hope this will come through okay for the people at home. So there's the always sort of in the bass, if you want to think about it that way. And then I can't really personally separate out the middle and the top. It's all just sort of, there's clearly some chipmunky stuff going on. But I have actually checked, and this does really have all 3 of them. If I leave either of the top two out, it sounds different. So I do believe that I did it right and that this is just what it sounds like. Oops. And you can definitely hear a doom, doom. There's like a double pattern in the top, which is presumably this, especially with this long space in it, it probably makes for a very strong pattern. And this is then reinforced by the space here. Whereas this space is kind of covered up somewhat by the sound here, and this space is sort of covered up somewhat by the sound here, but this leaves a pretty strong space here and here. So always, one more time, because it's fun. And then as a longer one, this is the anti-disestablishmentarianism sound. Oh, actually, I should say, can you hear the sounds okay at home when I play them? Okay, cool, thank you. So if we do anti-disestablishmentarianism, it's longer, so it doesn't disappear as fast, but it's a similar effect. So again, there's kind of a strong two-part feel to it, and then a lot of weird chipmunk at the top. I mean, 2 times speed is pretty hard to understand on its own. 4 times speed is just noise. Like there is no human speech left in that. And so, you know, really the bottom is the only part of this that's really has any chance of being understood, especially when you stack it all together. But that's kind of a cool effect. It made me happy, and it gave us an exam question. So, yay team. So the next 3 problems are basically to do this. Okay. Are there questions about what this means before we talk about what the parts of the assignment are? Questions at home? Questions here in the room? Coolio. Okay. So the first problem is to write a function double and join that takes a sound and returns a new sound that should be that is 2 copies. I clearly left out a word there of the given sound end to end, each of which has had its frequency doubled. So that's where you're basically writing the code that takes a sound like this and generates this. So it doubles the frequency, 2 copies, sticks them together, okay? And that's sort of the core of the whole exercise. If you can do that, the rest of it's pretty straightforward. The resulting sound should have the same length as the given sound because we're taking 2 copies, each of which is half as long, and joining them together. And I would definitely recommend splitting this up by writing a function that doubles the frequency of a sound as a separate piece. And by writing, I mean, use one that somebody else already wrote. You don't need to write a new one. So you could use the one we did in class. You could use the one that's in the book. I don't really care. And then once you have that faster version, that would be this guy here, then you create a new empty sound that's the right length, the same length as the original sound, and then copy this into this twice, once here and once scooted forward half the length. And there are a lot of different ways to do that. And if people have questions, I'm happy to talk about what that might look like. But that should be reasonably straightforward given the things that you've already done. So does problem 1 make sense? Are there questions about problem 1? Questions at home? Going, gone. Okay. Problem 2 is to add 3 sounds. So this takes 3 sounds, and we can assume they all have the same length. They will in the way that we're using them, because what we're going to add is like this, this, and this. But add 3 sounds should be generic, and take 3 sounds and merge them together into a single sound by adding their corresponding sample values. And make sure you divide by 3 to avoid clipping. So you're taking 3 sounds, and for each sample location, get the value from sound A, the value from sound B, the value from sound C, add them together, divide by 3, and that's the value of the new sound that you're making. Okay. And then stack frequencies takes a single, so this stack frequencies brings it all together and does the strange little thing. So it takes a single sound S and uses double and join to generate the first doubled version, which I'll call T here. Uses double and join on T to generate the second doubled version, which I'll call U. So S is like this guy here, T is this guy here, and U is this one up here. Okay. So double and join takes S and makes T. Calling it again on T makes U. And we get these 3 things. And then we add 3 sounds to with ST and U, and that should give us the result. And then we can return that. Okay? And that's it. That's the exam. So, questions about the exam? The take-home part of the exam. Okay. Going. So let me say a little bit about Booleans quick, because we haven't done much with those, and do want to give an example. I mean, there's a bunch of examples in the book, but we haven't done a lot in class. So I want to do a simple example so that you can see what that might look like. Let's see. Trying to think of what would be a simple example. Let me share Jess. Okay, so first, note that we have true and false. Now, it's really weird that those end up printing as 0 and 1. And I think actually in more modern versions of Python, Jess uses an older version of Python. In more modern versions of Python, I think those actually are just true and false, not 1 and 0. But the 1 and 0 is representative of the discussion we had way back at the beginning of the semester about how a bit can either be on or off, 0 or 1, true or false. You can see here it's using literally the 0, 1 idea as how it represents Boolean values. So a true is represented as 1 and a false is represented as 0. We can do things like say, let's say, write a little function. So we'll write a function pat, and it takes an animal type and an is plural. And we'll say if is plural, we'll return the animal, else we'll return animal plus s. Now that's not going to make all the plurals correctly, like some things are es, and you know, mouse is going to turn into mouses, which is not the right answer for mouses. But in a simplistic way, this will make things plural if we ask it to, okay? So let's see, back up one. Oh, no, didn't want to go up that far. Come on, open up. There we go. So CSci 1201, 2020, 1109.py. Load, and if we say pet, dog is plural true. Whoa. Oh, what did I do wrong? Yeah, if it's supposed to be plural, presumably that's when I would want to add an S. I just got my cases mixed up. So that's what I get for going too fast. That's likely to look better. Dogs. Single dog. Cats. Single cat. Mouses. Oops. But you know, the program did what it was supposed to. That's just what it did wasn't right. But it works fine if there's only one mouse. So we can use a Boolean like this, and you can just say if the thing, and that works fine. You could also say if is plural equal true, if you find that more readable, but that is longer and typically considered less preferable. But it would not be wrong. Yeah, this would be what that might look like. And so that's useful on the list exercise for deciding whether you want to use an OL or a UL on your list. Be careful that you get it right, the order right, like I didn't the first time here, because you don't want to swap and have OLs when you mean ULs and vice versa, but it should be pretty easy to test that. Questions about that? Questions about any part of the exam so far? Okay, So are there any questions on the take-home exam before we talk about some of the questions that people shared Friday about sort of just general questions, some of which are potentially relevant for the in-class exam? We got about half an hour left, so that's good. Okay, so there were a number of questions about wanting to see some more HTML stuff. And unfortunately, they were mostly vague enough that it wasn't clear to me what that meant, whether people wanted to see more like about HTML as an idea or more about using Python to generate HTML. I think probably the latter mostly, but it wasn't super clear for most of the questions. There is actually quite a lot of material on this in chapter 13. So chapter 13 is called Making Text for the Web, and it's mostly about writing programs to generate HTML. So there's a lot of examples there. I can certainly do more examples here if that would be helpful. It's not obvious to me what those examples would look like, but we can make stuff up. So we're going to hold that for a second. And we can come back to that if people have sort of more concrete versions of that they want to talk about. So there were questions about Python data types, actually. And so the phrasing was, love to know more about Python data types, especially lists, tuples, and floats. And floats are sort of different from lists and tuples. So I assume that sort of lists and tuples are here and floats are there. We haven't talked formally about tuples very much. But a tuple in Python is actually pretty simple. So we can have a group of things in round parentheses, not square parentheses. And these look pretty similar. And so a reasonable question that we haven't talked about around these is, what's the difference between them? And one of the key differences is the list can be made longer. So if L is a list, L is a bad letter, we'll call it X's, is 1, 2, 3. We can do things like append. Oh, that actually appended the whole thing. So I should have just appended a single thing. Well, whatever. So we can add things to it. And we can also sort it. So if we go back to X's, let's do something that's not in order. We haven't talked about that, but that exists. And so it'll sort things. So lists can sort of be changed in interesting ways. Tuples cannot. So if we have a tuple, you can't append 4 onto it. A tuple is what it is. It doesn't get bigger, it doesn't get smaller. It is a pair, it is a triple, it is whatever it is, and doesn't become something else. And you can't sort tuples. They don't support that kind of thing. So a tuple is meant when you know exactly how many items. Oh, and there's another important thing that isn't really, so you can have, in a list, you can mix types if you want. Oh, yeah, right, true turned into 1, that was weird. You can mix types. This is actually typically kind of dangerous because if you have a for loop, you say for y and y's, now you have no idea what y is. Sometimes it'll be a number and sometimes it'll be a string, which makes it very awkward to work with. So you typically, Python doesn't prevent you from doing this, but you should probably prevent yourself from doing it. It's generally a bad idea. And so if you need mixed types, that's usually a circumstance where you know exactly what things you need. So we might have like a student record might be a first name, a last name, and an ID number. Now, there, because everybody's going to have a first name, a last name, and an ID number, although let me tell you, names are really a pain because some people have middle names and some people have two last names, and some people, in some cultures, the surname goes first. I mean, it's easy to think names are easy. Oh, they're not. But let's pretend a very simple sort of, Kansas naming system where everybody's got a first name and a last name, and everything's well behaved. So here we know the first thing's always going to be a string, the second thing's always going to be a string, and the last thing's always going to be a number. And so we know by position what to expect. And we would never loop over a tuple. We would go in and get the piece we need. Okay. So with a list, you don't know how long the list. If you're handed a list as a function, you typically don't know how long the list is, and you would typically for loop across the items in the list as a consequence. With a tuple, you know exactly how many things there are in the tuple usually, and there's probably some agreed upon understanding of what kinds of things are going to be in the slots. So there'll be a tuple, it'll have 4 things in it. The first 2 will be numbers, the third will be a string, and the last will be a goose, right? And that's something we agreed on in advance, so I know how to take the parts out of the tuple. And the last thing that's kind of nifty is with tuples, you can do what's called pattern matching. So you can say open paren variable, comma, variable, comma, variable equals a tuple, and it will take the tuple apart and assign the parts to the variable names that you provided. So A is Nick, B is McPhee, and C is my ID number. So we could have, a better example would have been first name, last name, ID number equals student record, and now first name would be Nick, last name would be McPhee, and student, ID number. Would be 1, 2, 3, 4, 5, 6, 7, 8. So that's actually a really useful trick for taking apart tuples. But it only works if we know, again, how many things there are. I'm not quite sure what's going to happen. If I say AB equals student record, does it just drop the last one? No, it doesn't like it. And I bet if I do ABCD equals student record, probably won't like that either. Yeah. So you've got to have the right number of things if you're going to use the pattern matching. So again, there has to be an agreement that this tuple is going to have this many things, right? Whereas lists are more general in terms of length, but in some sense less general in terms of type, because you typically want all the things in a list to have the same type. If they don't, it becomes very hard to know what to do. And you can actually have a bunch of if statements that are like, if this is a string, do one thing. If it's a number, do another thing. But that stuff is ugly. That gets bad really fast. And so it's best avoided in general. So I don't know if that helped with the tuple list thing. Cool. And then I wasn't quite sure what the question about floats was. You want to clarify? Or oh, okay. So a bit more about when you would use a float, when you would use an integer, and what the advantages and disadvantages are. So the main thing here is, I really should have put this in I'm going to put some of this up in the file so it's available later. So floats versus ints. Integers are precise. 3 is always equal to 3. Floats can be weird sometimes, where you might expect, pi divided by pi to equal 1. But so we would want but it might not be because of rounding errors. So when you get into floating point numbers, you can get some weird things where if you do enough math, even though in theory you should come back to where you start from, you may not, because you may get back to the end and you're off by a little tiny bit. And this comes from problems like, I say 1/3 as a float, that's 0.33333333. Now what that really is an infinite number of 3s. So you may remember from some, math class in the past that this is a infinitely repeating decimal. It has no finite representation as a decimal number. So this representation is not exactly correct. The error is very small, right? It's, a bazillionth of a part off way down here at the end, but enough bazillionths can add up. A grain of sand is a very small thing, but if you have enough of them, you can get a beach, right? And so little things can matter in large enough quantities. And so you've got to be a little careful with floats that sometimes when you expect things to be equal, they aren't. This never happens with integers. So integers are really nice because they're well behaved. We don't have to worry about this business. You can also get some strange things in number land. So if we say 1 divided by 0 is an integer, we get a simple error. Now, oh, we get it here as well. Okay. So there are programming languages where actually 1 divided by 0 would be 1 divided by 0.0 would actually be positive infinity. There's a representation in floats for positive infinity. And there's also a representation in float for a thing called nan, which stands for not a number. And you can get weird things where 0.0 divided by 0.0 would get a nan, because this is neither positive infinity or 0. It's something undefined. And so you can get some weird stuff like that. And again, that kind of stuff doesn't really happen in the same way in integer land. So we like integers because they're precise and they're well behaved. But there are times when what you need is a floating point number, right? I mean, that's just the truth of things. If you're doing an engineering project or a physics simulation or something like that, floating point numbers are the right thing to do. And so, you use them. Interestingly, money is often not done with floats because of the precision problem. Money is often done, like, say it's US money, you might store the values as whole cents. So a value like $37.48 might be stored as 37.48 as the integer 3748 to avoid rounding problems. Because again, if you're a bank and you have enough customers and enough transactions, if you store everything as a float, every now and then something unexpected is going to happen. You know, the odds of it happening in any particular action are very small, but you scale that up across the probably billions of transactions that a major bank processes in the course of a day or a week or a month. There are going to be some weird things happen. And so they have to be very concerned about their representation issues as a result. Not that we really care, but integer arithmetic tends to be a little faster than floating point arithmetic. Most computers can do a math step on integers in one time step. So the processor in your computer, the CPU, it has a clock, an internal clock that says, okay, ready, go, ready, go, ready, go. And every go is execute the next instruction, whatever the next instruction in the program is. And the ready, go part is really just letting electronics settle out. There are weird transients that happen on wires, and we just don't care. This is not a physics class. But the clock allows us to not have to worry about some weird problems with actual physical electronics. And the speed of that clock determines how fast your processor goes. So if you're buying a processor and it's like 2.5 gigahertz or 8, well, nobody's selling 8 gigahertz, so 3 gigahertz or 2 gigahertz, that is how fast the clock goes. So a gigahertz is a billion instructions per second. Yes. So a 3 gigahertz processor is doing 3 billion instructions per second. That's an enormously fast thing. When I started here at UMM 30 years ago, processor speeds were still measured in kilohertz, so thousands of instructions per second, and we were just getting into the low end megahertz, so millions of instructions per second. And we went from that into the gigahertz in a decade and a half. It went very quickly. And then we've been sort of in single digit gigahertz ever since. We've sort of run into some problems, basically of physics, that make it hard to make things go a lot faster. But if you add two numbers together, you're using one of those clock cycles. If you add two integers, sorry, you'll use one of those clock cycles. So if you're just doing integer arithmetic, you can do about 3 billion integer adds in a second. If you do floating point numbers, you're probably using 2 to 4 clock cycles to add two floating point numbers. Depends on the details. And we are not going to get into those, but it's slower. That's the important thing. So a floating point add is typically going to be slower than an integer add. So it's a little slower. Now, it's a little slower at a level that you will never actually see unless you're doing very high-end number crunching. But it is a little slower. And there's the precision problem. And so that's kind of why we don't just use floats all the time. Because you might think, well, you know, if we just have floats, then we get integers for free. 3.0 looks like a perfectly good integer. So why not just always use floats? And we don't always use floats because the precision problem primarily, but also the speed problem. So does that make sense? Questions about that? Good.
So what about when testing these two floats? Can we do that in test?
Yeah, we certainly can. So the question, because I don't expect people at home heard, is can we move from floats to integers and integers to floats? And we certainly can. So if we say int 3.7, that'll work. And if I copy that and I paste, oops, no, my copy paste failed. It will just throw away the fractional part. It didn't round, which you might have thought it was going to do. It just literally dropped the fractional part. So int of 3.7 is 3. You don't really have to go the other way. Let's see. Let's notice that if I added an int to a float, that turned that into a float. And if I wanted it to be back to an int, I would have needed to use the int thing again to get it to come back. So basically, you do math with ints and floats, it'll turn everything into a float and do the math in float land. And you can you can convert any number to a string, whether it's a float or an integer, with the str function. And you can say float of 3, and it'll just turn into 3.0. So you can convert integers to floats that way. Did that answer the right question? Okay. Cool. So yeah, you can use the conversion tools in integer, float, and stir to move back and forth between these things. Now, if you try to use so that works, that will fail. So if you try to read a string that isn't an int, that's a float, it will fail on you. But if we try to read it as a float, it will work. You might have thought that this int would just give us the 3 and then throw away or ignore the 0.7, but it doesn't actually do that. It needs it to actually just be a straight up int. Now, we can float without a decimal point, float 3, that'll be fine. So float doesn't require that the string have a decimal point or a floating point part, but int requires that it not have one. So, does that help? Questions at home about any of that? Oh, gee, we don't have a lot of time left. I get excited and I start to talk a lot. Let me see if there's something else easy we can do. Okay, so there's a question I had hoped to get to, but I don't think we really have time to do it well at this point. So maybe I'll post something online about it. Somebody had a question about there was a question on the first exam about the parts of a function, like what's an argument, what's the function name, that stuff. I think that's an important question, and I would like to say something about it. So maybe I'll post a page on Canvas today that sort of takes that apart. And then people can ask questions about that. There's also a question about putting images and sound together to create video. There is actually a whole chapter on this. So chapter 14 is focused on videos and animations. And normally we would actually do an exercise with that. And we're not going to because we've just run out of time. And there's other stuff that I really want to make sure we have a little time for that are in the last 2 chapters, so 16 and 17, because these are pretty important things that I want to talk about a little bit. And movies are fun, but they don't introduce anything terribly new. Because if you think about it, a movie is just a sequence of images. We know how to do images, so you just make a sequence of them. And putting sound on top of that is mostly a matter of getting things to line up. But there's nothing sort of fundamentally hard about that. It's tedious in places, but it's not like fundamentally difficult. So I think we're going to skip that in order to save a little time for some other things that I think we need to talk about. And then there was a question I didn't fully understand. Well, I think I understand it. So question is about upper. So if we have a string dot upper, we get Morris. And the person asking the question said that they sometimes got that you couldn't do upper on a list, but you can do it on a string. So if you have a list of characters, you cannot do upper on that because upper, the thing to the noun to the left of the dot must be a string and cannot be a list. So if you want to upper a list like this, you'd have two options. You could turn that list into a string and then upper it, or you could loop over the list and upper each piece one at a time. And it depends really on, is your goal to have a string at the end or a list at the end? If your goal is to have a list, probably doing it with a for loop makes more sense because then you'll still have a list when you're done. If your goal is to have a string at the end, then it's probably easier to turn it into a string and then upper the string. So you could, for example, if we say m equals, grab this, so m dot upper will fail. Can we do this? Nope, that did not work. But we can do join m. That'll make a string with nothing in between. And if we join m and then say upper, we would get the full uppercase version. So that would be a way to solve that problem if you wanted it to be a string. If you didn't want it to be a string, then you're looking at something more like R is the empty string for C in M, R equals R plus C dot upper, boom, and that uppercase, oh, but I still made a string. I actually really wanted that to be a list, didn't I? For C in M, R dot append, C dot upper. Oh, probably. One more time. And then we should stop because class ended. For C in M, R dot append, C dot upper. There we go. And then we get all the letters uppercased. So I don't know if that answered the right question, but hopefully that was helpful. And we've run long, so I should be quiet. So we'll have the in-class exam on Monday. If there are any questions between now and then, hit me up by email or Slack or whatever, and we'll have that done. So talk to you all later. Ciao. There's stuff there. And